Hey everyone, this is Dr. Walker. In this video, we're going to go over the first example from v578 on Ampere's law. In this problem, we have a thick wire rather than a thin wire, and we want to find a magnetic field outside the wire and inside the wire. And we're going to use Ampere's law. So first, let's take a look at the case where R is greater or equal to than the radius. So we're looking at regions outside the wire. Let's write down Ampere's law, the line integral of B dot ds is equal to mu naught I, where I is the current penetrating that surface made with that Amperian loop. Okay, so we have a cylindrical wire. We want to pick an Amperian loop that takes advantage of the symmetry. So just like we did with a straight wire in the video, we're going to pick a circular loop because we know that this current generates a magnetic field that is also circular around it. We know that when we pick this Amperian loop that it has a certain radius r, that the field will be constant along this loop because we're at the same distance from the wire. So the B is going to come out of the integral. The dot product is going to vanish since B is going to be parallel to ds at all times, where ds is a line segment along that loop. We know that using the right-hand rule number 2, if we put our thumb in the direction of the current pointing towards us here, that our fingers are curling counterclockwise along the direction of the field. So they're parallel, the B and the ds. So we have the integral of ds along the closed loop, and that's going to be the circumference of the circle, which is going to be 2 pi r. So you see how the process here is very similar to using Gauss's law, where with Gauss's law this was an area rather than a circumference. And then we have mu naught and I, and we can solve for B. B equals mu naught I over 2 pi r. And in all of these problems, we're just finding the magnitude of the field because its direction changes at all times, so that would be hard to express the direction. We're just finding the magnitude of the field. So if you're away from this wire, the magnitude of the field is going to be the same as if it had been a thin wire. Go back to Gauss's law. If you had a charge distribution that was spherical and you were looking for the field away from it, remember how it was just like the field due to a point charge. So very similar here. Now let's look at the case where we are inside the wire. R is smaller than R. We're going to set up Ampere's law again, the line integral of B dot ds equals mu naught I. We're going to pick an Amperian loop that is circular inside our wire, and it's going to have a radius r again. So for the left-hand side, we're going to get the same thing, B times 2 pi r. But now we have to be careful finding our current enclosed within this loop, or penetrating. How much current is penetrating here, the surface? It's not the entire current, right? It's only a fraction of it. So one way to find the current enclosed within this surface is to, let's call the current enclosed in this surface, let's call it I prime, is to take the ratio of the current enclosed within our Amperian loop surface here over the total current I, which goes through the whole wire. Let's take that ratio. And remember that we can write current as current density times area. We are told that the current is uniformly distributed, so that means that J is constant. The current density is constant. So this is the area here enclosed by this Amperian loop, and then A without the prime is the cross-sectional area of the wire, this area here. So J is constant, so it cancels out. And the area of the little loop here is pi r squared, and the area of the whole current wire is pi r squared with capital R. So the current enclosed ends up being, and the pi's cancel out, ends up being little r squared over big R squared times the total current. This may look like a long process, but let's go back to Gauss's law and remember how we used to do this type of problem. Let's say we were trying to find a field inside this charge distribution. Do you remember that when we used Gauss's law? E dot dA equals Qn over epsilon naught. Remember when we found Qn and we said that if the charge was uniformly distributed, just like this current that's uniformly distributed, we said that the charge inside was the fraction of the volumes. We said it was the volume of the Gaussian surface divided by the total volume of that charge distribution, and it was the ratio of those volumes times the total charge of that charge distribution. So ratio of volumes times charge. Well, here it's a ratio of cross-sectional areas times current. So similar ideas, if you can make those relationships, it helps you understand it a little bit better. So for the current enclosed, we're going to have little r squared over big R squared times the total current. And now we are ready to solve for the magnetic field inside this wire. It's going to be mu naught r squared over big R squared times I divided by 2 pi r. So one of the r's will cancel out. And we're going to get mu naught r I over 2 pi capital R. The magnitude of the magnetic field inside the wire, while mu naught I over 2 pi r is the field outside the wire. Next video, we'll do an example where the current is not uniformly distributed, just like we did with Gauss's law when we had the charge was not uniformly distributed.